for here. So now I will continue to talk about the machine learning, and this time I will introduce one of this classification. So this classification, which is very typical problem in the machine learning. So okay, now let's discuss the regular let's discuss this problem. This is a regression problem, which is this is very important problem. So for example, if you want to do the stock price prediction, the house price prediction, or other price in ending up, you know the prediction any value from the different data, from the different factor that you will lead the regression. So in the regression, suppose that we have the we giving a training set of the observation again. Also mean the training the data. So there's here which are the bulldog. Yeah, you can see here there's many bulldogs here, right? There's bulldogs, and yes, this is x1 to xn, right? X1 to xn, as yi to yn. This is yi, right? This is x1 to xn as yn to yn. So this is binary classification problem. So y is negative 1 or 0 or 1 or for example some 0 to 10 if the digit classification problem. So but in the regression, y is a real value. Y in the regression, remember, y is a real value. Okay? This is real value. You continue, it can be nice. For example, if a stock price, a stock price, right? House price, right? Y can be house price, can be stock price, right? Well, for example, like the house price, it can be a 1 million, 2 million. It is a real value, right? So give so this y and this and give this x and this y regression problem. So I want to predict a function that can fit this data, and then give me a new input point, for example x and plus 1, and I want to predict y and plus 1, right? I don't want to provide this. I want to predict the new value based on the new input. But it has a similar train of the previous inputs, right? So the regression process is to estimate the y from estimate the y x from the data. So k so here so the so again here the k. So again the k and k can be used for regular problem, which is the simplest one regression algorithm. So for each test point, we want to find the case in okay. When the classification is easy, right, for the new test points, or just find the k labels and do the working, right? Before that, therefore do the working. Therefore, the k-nearest regular so the k-nearest regression for each test point x, we just need to find the k-nearest. Okay, x, right? We just x here, x we just need to find the k-nearest. The simple xi in the testing in the training data we need to load their value yi, then the output is just the mean of the value, right? This is easy for the classification problem. We just need to label, so we do the voting. So the regression problem, we need the value, so we do a average, right? So we the output value of the yi is actually the average of all the KD's labels of the new inputs x. So xi. So again, we need to choose to actually learn the k, right? So we want to choose k. So here n equal to 100, right? N equal to 100. That means we have the 100 training example, right? And again, we need to choose the value of the k, right? So we give the k to we need to choose the value of k to give me the best accuracy of the prediction, right? So let's try the example which is a polynomial, which is a polynomials curve fitting. So polynomial curve fitting. So this is the green curve. This actually the true function, right, which is not a polynomial, actually is just a wave curve, right? So the data are uniform in X, right? So from 0 to 1, I have 10 points here. From 0 to 1, I have 10 points here, right? So start from the 0, 0.0, and then 0.1, 0.2, 3, 4, 5, and then and the y value is actually different, right? So y value is not uniform, and actually we have some noises, right? Okay, so some value actually lost on this perfect function. So we will use a loss function. That's matter the method the squared error, right? So the squared error, right? So this is actually we use loss function. So in the prediction prediction y x from x, and then loss from the red polynomial is the sum of the square, the sum of the square, the radical error, right? This is radical error, means the sum of this radical error. So basically, let's assume that I already get some function y, right? So then input x that the value I predict by using my function, and I use this function to minimize the target value, which is the ground true value, right? So if this value is quite big, then the that means that this y is this means this function is not good, right? So I want to use this kind of loss function to optimize my learning progress, to get the best function, right? So why so that's why because we assume that this is actually a poly so this is actually a polynomial classification regression function. So I assume that's y x w, right? X, this is w here. So y x w, this function is a polynomial. This is a polynomial function. You know what is the polynomial, right? Right. I will not introduce here. So basically the w w0 plus w1 x and then x plus w2 x squared and then until xm xy the powers of the m, right? This is a typical polynomial function. So I assume there's the polynomial function can fit this data. So that's mean in the learning process I want to learn the parameter from w0, w1, w2 and to the wm. I want to learn this parameter from those data. When I got the testing data, I just need to input my x input the w I learned from the training data. I can predict the value, right? So that's a function. Assume that to train this one, I need some loss function, and this loss function I just define with the loss function. If this value is big, it does mean the power, because SI is the facts, right? If I have the testing that the SR is facts that we the W can be trained. So if the value is big, that means the current W is that means the current W is not good enough. So we need to adjust my W a little to make sure this value as small as possible. So if you if you learn some machine learning before I see my video, you may learn you have learned you maybe have already learned the optimization before. So what we want to do is to use the training data to minimize the loss function, right? To minimize the progress of the minimize the process of the minimize this function to get the best W, to get the best parameters, right? That's a learning process. Some phase some phase surface data to the data which is the best. So let's assume in the polynomial function we have the one super O have the higher parameter, which is m, right? This is m. So a high parameter which is m. So it is decided to capacity of this polynomial function. For example, if x equal to 0, that means x, y, w is just w, just a w0, right? Just a single straight line. So of course this line is not good enough to fit the data, right? So think about it. If this is the function you learn, then you give me the x, for example, give me a well, if x equal to 1, I can predict the value, right? It's okay. But if x equal equal to, for example, this is 0.6, right? So so maybe here 0.6 here, right? If that function if that is a function, that's what would be the error would be exactly x, right? So that means if I equal to 1, it is not good one, right? right? Because this equal to feed to because if n equal to 1 and if m equal to 1, and so the yxw will equal to w0 plus w1. So the actually is straight line, right? Here, if m equal to 1, this is actually a straight line. Into two-dimensional plane, it just be a straight line. Then the straight line, of course, is this line can be moved depends on the parameter w, right? So depend on the w parameter w we learn, but that no matter what the angle it is, this is not a good fitting of the data, right? So this is not good enough. But if m equal to 3, we have a good if we have good algorithm, if we have a good learning of the w, and actually that we will be the polynomial function, and actually you can see it's very close to the true function, but some point is m equal to line, right? So although it can fit each point, right? Very well. So but it has a big difference between the real function. We want to predict and the underpredict function, right? So the big difference, and that is big difference. So although it can fix the training data very well, but if we have a new data, for the example, for example, if we have the 0.2, some value between between 0 and 0.1, for example, this one, this is true function. This value, that's one true value, but if I use the predict to predict if f, the value will be here, right? I predict the f, the value will here. So that means it is not a good prediction. So we call this actually is overfitting. So this is the actually overfitting. This fit the training data too well, so it's overfitting. But they test a little generalized ability. So he report the actual error. So we can see that from the training when we have the different m, right? You have different m. This actually actually slightly the error becomes slower, but when the m equal to 9, right? When the m equal to 9 here, the errors become 0. This is the test for the testing data. This is the test for the testing data. Well, the train is smaller to the training sets, but this is super big. The error is super big. So this is training data. This training data, the error is very low. It's 0. But for the testing data, the error is super big when the m is 9, because we overfitted the training data. Okay, so the training errors go to 0, but the testing error increase with the m. We need to have trade-off between the model compatibility, the accuracy. So if the model has many angles of the freedom, as a data, this can fit the training data perfectly. For example, in our last cases, the polynomial cases, if m equal to 9, we can have very complex polynomial function, right? So it is it's a nice a w0 plus a w1x until w9. So x y powers of the line is a super, right? Super complex polynomial, right? And we have 9 parameter. The pi is not the parameter to left is, right? The pi is not a parameter, okay? To left. So when m equal to 9, of course we can fit the training data very well, but we cannot produce a good result on the testing data because it's overfitting, right? So we can see the objective of the machine learning generalization ability, right? Finally, we want to use the most on the testing, but lot on the training data. So we need to be careful of the generalization ability. Yes, yes, we can expect the model to generalize well if it's by the training data. If we pay the training data surprisingly well, give the capacity of the model, right? So if the model capacity, so the basically we want to find the right capacity of the model, right? Sometimes, of course, the model is if the more complex, that means it can train the training data well. But it cannot generalize well to the testing data. So here is an example. So from m to 9, m2 equal to 0, and then m equal to 9 of the polynomial function. If we learn the parameter from w0 to w9, the polynomial function, we can actually find when the m equal to 9 to some of the coefficient, the w is super large, right? That's a signal, a sign of the overfitting. That means the function is fit to the training data very well, but impossible to have you know a good generalizability because some of the parameters are so big. So to prevent overfitting here, two ways. The first way is as more data. The model capacity, for example, if n equal to this is so nice. This is for line of the order of polynomial, right? So in the previous example, we only have 10 data point. We have set that m equal to 9, and you still remember, if you still remember the polynomial function is very different from the true function, but here we simply just add the 5 more training example, and m is still equal to 9, and then we learn the length function actually become this sign equals to the training function, and actually we create the training example and equal to 100. Even m equal to 9 is a complex function, but you can see the length of the length function match to the ground truth function very well. one way to prevent overfitting is to provide to improve that give more number to the training data. That's why actually we always say for the machine actually nowadays this model machine learning is based on the data set, right? So why people prove that deep learning works so well, you know the deep learning like a C, and as I mentioned, we always have millions of parameters of even billions of parameters. In here we only have the line polynomial, line order polynomial function, just line value, just not think about if we have the 1 million of the billions parameter. If we only have 100, so it's impossible to train a good model. It's definitely overfit of the training data, right? So that's why in the deep learning method we normally require of training a lot of training data for the image set. There's a million of the input and millions image, and to train the transformer to train a bird. Right? People use of the 10 GB of tests from the online, and right. So there's so people use so many data to train deep learning model, because we are independent deep learning model, we have so many number of parameters, right? So there's one way to prevent overfitting, and more data and more field and more data, and you have a better prediction and better how competence of your function is of course is compressed function, right? So can fit your data well, because as you can see, because as you can see here, let me see. So no matter how many data you have, you cannot fit the training downtime, right? Because you load m equal to 1, you just have a straight line. If m equal to 0, just a flat line. No matter how many data you have there, no direction to modify it, right? So you have found the best capacity of the model based on your data, right? So this one way. So that's one way to prevent overfitting of. So in your so if you create your project, if after see my video, if you want to create your own project, for example, you may you want to prevent the overfitting. For example, you will say, well, my data set is enough. Well, you say my data is enough. Train 100 example for training, and I hope you say well, because maybe most of us cannot download a big data set, right? Um, um, Maybe when you when you learn the machine learning by yourself, when you try to create simple program, little machine learning program to test the data. So you do that. I prefer don't need to download the big data, right? Because we don't have a good machine to process those numbers or data set. So you can collect the data by yourself, right? So I think when I learned the machine learning, I maybe I just train 100 example in the case. Really impossible for you to learn some complex model. So make sure that you don't use the deep learning model. You can just use the KNN, because less complex model, right? Or, so if you have a question, maybe you have a question, what about when we use the pre-trained deep learning, right? The other case, this is other thing, right? That's if you have this one, that's equals one. That's so in the pre-training deep learning model. That's because pre-training model has been trained very well once large number of the data. So and prove the same for the deep learning. And also a good thing of the deep learning model that is that the generalization ability of the different model is a super good. So that means if you bring the train or deep learning model on data set and actually test your deep learning model like the cell C, whether the data set and C variable image data set, right? Then the performance actually is okay because the generalization ability of the deep learning model is good, and the generalization generalized ability of that is good because it's trained on large number of the data, right? So that's a different story. And in the later video, maybe I will introduce some deep learning basics. Okay, so actually, if your data set is super small, you cannot fine tune once, and once you do the fine tune, actually it will overweight, right? So the other is but for this one, if you don't have the big data set and if you want to train from the scratch, right? So where is the training? We normally say train from the scratch. We don't consider the plan training. If you want to train from the scratch, make sure you use a less complex model, right? If you have, well, for example, some of you may I have a good machine, I have a good CPU, I want to work on the image processing, and I have some millions of some image, nice open image from the website, and I want to train a big model of okay, you can use complexity model. And in that case, actually, you can still use the plain training model, and you can save your time of training, so that other story. So I think that is other story. So um, so machine learning model, about the machine learning model, other machine learning model. So the data is very let me see. The data is very valuable, and sometimes you can expensive, right? Because you need a lot some maybe some because some model is so compactly, so it's so expensive you cannot get it. So other way to prevent overfitting, let me talk continue. So I introduce another way to prevent overfitting. It's called regularization. So you penalize the logical efficiency, right? The value, for example, over here, when I equal to 9, if I only have 10 points, and that's a parameter I learned from those 10 points, and some parameter super big, that's not a good size, so we can penalize this situation. We can, well, we don't want this value. If this value is too big, well, this is not a good direction to optimize. So that means that I can add a penaltative value here. This is a penaltative value, which actually absolute. This is actually the absolute value of the W is a parameter. Absolute value of the W is a square. So that means if your W is super big, that this is 1 million, and and the square is super big. If you square is if you square is right here, if you square is maybe super big, right? So because this is loss function, that mean by plus in this one, your loss function, which will be super highway. The loss will be super highway. So your loss is super high. That means it's not a good, right? Right. The way to do optimize, right? I don't want I don't want to introduce optimization too much in this video because it's too complex. It's more complex. So you need to know that if this error function, if the loss function is too big, that means the model cannot be converted. That means the category cannot be converged. You have to you choose some low parameters. So you can see they have another hyperparameter, which is lambda. To this lambda, basically decide how much power you want to choose to penalize this this coefficient value. So in this sample, you can in this one you can use the validation data set to choose the lambda, and you can see even you only have 10 points, and when we equal to 9, and if we set lambda equal to minus minus 18, let me see, coefficient value, yeah, okay, you see. So we actually get the function. So you can set a different value. So this is a law, and lambda, other lambda is a long lambda, right? So that's why negative value. This is negative value, right? So okay. So the other way is still to be, the overfitting problem are introduced this one because introduced before, because you may find that even if you guys have already learned the SVM, you may face a problem of the overfitting. And I mentioned it before that even the SVM also have overfitting. So so that's why I think later in the later video I will introduce some hyperparameter you need to tune that your validation data. So you guys may find some problem. For example, you got 99% accuracy on your training data, but use your models on the testing data that actually is super low, just 2% or 3%. So you may ask what's problem, right? So the that is the reason. Overfitting is a reason. So you need to check the model whether you set the right regulation lambda. So if you use for example use the polynomial function, if you use the SVM, if you learn the SVM, I will introduce SVM later. If you using SVM in here, even in SVM we also have this how to say we also have the penalty, right? We call the regularization term. We whether to check whether you set is right parameter. You don't know what happened. If you don't know what happened of this algorithm, maybe you can try to see some explanation of the penalty. From the table, okay, you can see if the lambda equal to minus infinity, it is it's not the previous value we learn from value. Some parameter super big, and actually the lambda equal to minus 16 as become becomes very normal, right? Some parameter you can see if the lambda equal to minus 16 is become normal, but if the lambda equal to minus infinity, that's the value is super big, right? This value we had to add the penalty on it, right, to minimize the loss, right? So I mean the generalization ability of this one. So the generalization ability of this one is minus 16 is in minus 16 is much better, right? So if the minus is 16, if your generalization ability is good, so just something like that, right? It's very smooth, right? So this is one way to deal with the overfitting. Yes. So how to set the parameter? Actually, introduce this one. It means that you have to divide the data into 3 subsets: training data used for learning the parameter of the model. Validation data is not used for learning, but used for decide what type of the model and what amount of the regulation works best. So, for example, for the Keynesian neighbors, you can use the validation data to the right. For the polynomial data, you can use the validation data to choose the lambdas and m. So the lambda and two parameter in the hyper parameter in that model, and testing data it get the final unbiased as estimate of how well the leading machine works. We accept so actually we can expect this as estimate to be worse than on the validation, right? Testing. Because the validation data you test is several times, you will find the best value. So we accept the estimation to be worse. So, but on the testing data, you cannot have you just test this one, right? So the value use the hypermeter high length from the training data and the validation data, and test on the testing data, and you have your own data set. If you download existing data, for example, you download the ImageNet or download the Cocoa with another image, right? So dataset, if you download some NLP dataset, they already have official speed. They already give you the training speed that the validation speed validation because they already give you training speed the validate superiorities, and there a test speed, and for some test data actually like for example, I'm not you are working on the research question answering, which is area you have the image and you have the natural language customing, and your model want to answer the question in your area. You actually you don't push the testing data, right? We keep the testing data as a secret. We put this on we put this on yours. You put it on your own server. If some people only train the the machine learning on the training data and test it, and already it on the validation set, that if they think their model is good enough, they submit their result, the model to your test server. So if they already give them accuracy, that you got like something like 78% accuracy on your testing data, but in the testing data, right? Because testing data is come from the real world, right? Real world data, you only test one. So if, for example, if in the company, if in the software house, if you give your testing model to the client to test it, right? They won't let you know the testing result, right? They never tell you. They just use it, right? They will find that finally they will just find that maybe this system is not accuracy. So how to say, we keep test data on our I suggest we should keep test the data on our own server, and they ask the candidate to submit their result, right? But maybe some kind will not help you to save the result, will help you to submit the testing result for you. But in the test we never use the testing data, because you have to in your case, if you have your own kind, it definitely split into the training, validation, and the testing, right? Okay, but the testing data environment, the testing data should be come from the actual environment. Okay, so this is generalization problem in the classification, which is very important. This is definitely it's very important. So well, think about the polynomial function. If m equal to 0 is just a fit the line, right? Just a straight line. It is impossible use what's the day? Let me go to see the graph. It's not here. Okay, so in the generalization problem, if m equal to 0 is just fit the line, right? So it is impossible to use that a simple function to classify the sun gases. You also compare the data, right? So it's called underfitting. So sometimes we have overfitting problem. So the function is so compact, it can fit the training very well, right? This is overfitting, training very well. This is underfitting, right? So, but go to test the data, but so it can fit the testing training data very well, but go to the testing data, but the distribution may slightly different. So the accuracy will be actually low, right? So a wide overfitting. So if you meet the underfitting problem, try to improve the complexity of the model, right? In here, if you got the underfitting, try to improve your complexity, right? Improve the complexity, right? Not improve your complexity of your model to make it worse like this. So if you have overfitting here, right? As I mentioned before, it's too complex. You can decrease the parameter. You improve the increase the number of the data point, or you can add some regularization, right? You can add some regularization. So why is overfitting? So finally, we want to got some model like this to fit the data, but they have some generalization ability. This is case of the classification problem. So well, this is about the optimization. Actually, I don't want to introduce your optimization in this video, but maybe this is maybe I will try to introduce this optimization in other video later. So but this is not the part in here. But yeah, this if sometimes if we talk about SVM, also support the vector machine. Actually, we was the most classification problem you have. Even seen ever seen. So you have the the most classification problem you have ever seen. So we know that the Kn is simple, right? It's easy to use, but one problem of the Kn that is that you have to always carry your training data during the testing, right? Here the million training data is impossible to make this applicable on your phone or any application, right? So your phone, you want to recognize your face, right? For example, your phone. Let me find some cases. No, it's not here. I want to find the binary classification. Oh, I can't find it. It's not here. Okay, so for example, the binary classification, right? So we can have two situations. Maybe this one. Right. Maybe this one. For example, if you want to recognize your face, you think that this is compares many faces, right? You think about it. They have to compare many faces you have. So that's why we need some other more careful classification problem. Some classification argument, so the SVM supports the vector machine is actually one of the most one of the most classical one. Actually, before the deep learning method, I guess no one use the SVM because depend on depend on the deep learning model or CNN model and Lucas model. It's kinds of other classifier. So I will introduce in the next in the other video. But before that, the SVM is one of the most classical one, and actually if you can try use the SVM because this may have in because I suggest use the SVM because you may not have enough data, right? You may not have a good GPU to train or a deep learning model, but of course you can find the fingerprint training model, but well, if your data is small, still you can use the SVM, right? Kinds of really good algorithm to classify your data. So let's try this binary classification. Let's assume we were doing a binary classification problem. So let's just now I want to introduce a binary SVM. So the binary so the SVM again we can use that to solve the binary classification problem, or we can use to solve the multiple class classification problem is called multiple class as SVM, right? So here I only want to introduce the binary SVM. Okay, so try to imagine the function fxi. So that if the so ideally I so so giving a charming training data set s y y s x I y for I equal to 1, right? So to n, so let me see, let me try to write that. So give the training data xi I equal 1 to n if xi and yi. xi is a feature vector and yi because it's a binary classification, which means just -1 or 1, right? We want to learn the classifier fx such that fxi bigger than 0 if y is syi is a positive if yi is a positive one, and fx is more than 0 if y is a negative one, right? So that means give me a f function and it give me a new point of x, and if I input that one into the function, if the bigger than and the equal to the 0 is a positive class, if they are similar, then 0 is negative class. It is a classical binary classification problem, and if you move this one is not if you move this one this to the left side, so that means we want to do this yi times to here we want to do the yi times the fx are bigger than the 0 for correct classification. Okay, so the binary classification, so this is a binary classification. So we have two examples. For this example, we left the example A, right? So so we talk about this linear classification and non-linear classification. So for this one, we can draw a straight line should classify them into two classes, right? Like for maybe change the color, use the green color. You can use the straight line here, right? You classify them into two classes. Yes. So that means we can simply learn the linear classification to classify them. For this one, it is impossible, right? So low chance that you draw a single straight line to classify them into two classes. Right? That means sometimes we need a linear classification, sometimes we need a non-linear classification, right? So so this is a linear acceptable, so this is not a linear acceptable, right? So this, okay, so maybe I in the next video continue talking about the binary classification. That's the end of today. So if you guys like my video, please subscribe my channel and click the like button. Thank you, and